Right, continuing on with section 3.2, in which we discover the universal the universal gas equation. So when we're thinking about amounts of gases, they're influenced by their temperature, the pressure, and the volume. So making a reference to Lord of the Rings, like the One Ring in Lord of the Rings, there is one equation that brings all the relationships that involve volume, pressure, temperature, and the number of particles all together. So we've got all the famous people involved in gases or in Tolkien. Right, so just checking, yep, there we go. So the equation which relates volume to pressure is called Boyle's law. Now, you do not have to know these by name, but you do have to be aware of the relationship. So for a given amount of gas at a constant temperature, the volume of the gas is inversely proportional to its pressure. So as the pressure increases, the volume decreases, or if you like, as the volume increases, the pressure decreases. So volume up, pressure down. Now we can take this equation in the box and we can take the pressure across to the other side and we get the equality, pressure times volume equals K, which is a constant. Now, this constant is not any particular value and you don't have to give it a value. So don't worry about that. It's just that when we multiply pressure and volume together, we get a constant value, no matter what the pressure is and what the volume is, assuming that temperature is constant and the amount in mole of gas is constant. So then, if you have different conditions, so if you're going to change the pressure or the volume for your gas, but you keep the amount the same and the temperature the same, you get this situation, which should bring you to mind the equation from last year, C1V1 equals C2V2. Similar situation, P1V1, initial set of pressure and volume multiplied together gives you P2V2, the final set of volume and pressure. So here's an example where we use this relationship. We've got an observation balloon. It's got an initial volume. So we note to ourselves that V1 was 40 litres. The initial pressure was 1 atmosphere. Now notice the units don't matter here because it's a comparative equation. So as long as they're the same, so they're both atmospheres, then we don't have to worry that we're playing around with atmospheres. So P2 is our second pressure, our final pressure, and we want to know the final volume. So this is V2. So we plug those into the equation, which is rearranged. And so P1V1 equals P2V2 has been rearranged to V2 equals P1V1 on P2. There it is with the numbers, and we get 200 litres. Now, does that make sense? Always have a think about whether you've done things correctly. We started off with a volume of 40. It was at a higher pressure, 1 atmosphere. The pressure has been decreased, so we expect the volume to increase. Now, if you're good with ratios, you'll notice the pressure has decreased by 1 or 2/5 of its original value, so we expect the volume to be 5 times the initial volume. Temperature. Now, temperature with gases cannot be in degrees Celsius. We need it to be in Kelvin. So all our calculation temperatures must be expressed in Kelvin. The reason is that Kelvin doesn't have negative numbers. So if you start multiplying by a negative number, you could end up with a negative volume. And we all know negative volumes don't exist. So that's why we need Kelvin. So to convert Celsius to Kelvin, you take your temperature in Celsius here, and you add 273. As shown in the thermometer on the right-hand side. So we have 0 degrees here, and it's equal to 273. Therefore, negative 273 degrees Celsius is 0 Kelvin. Notice there's no degrees for Kelvin. It's degrees Celsius, but it's just Kelvin. So 0 Kelvin is theorized as the lowest possible temperature that can be reached. And in theory, at that temperature, everything is solid and all motion of particles has stopped. Next relationship is that between volume and temperature. This is a fairly simple one. As volume increases, temperature increases. Or we could say, as temperature increases, volume increases. That's probably the more logical one. As you increase the temperature of a gas, it's going to take up a larger volume because the particles are moving around more quickly, they're hitting each other, they're spreading out. So once again, this law, Charles's law, and once again, you don't have to know that it's Charles, just know the relationship. It can be rearranged to give us an equality. V over T equals K, and then the comparative equation V1 on T1 equals V2 on T2. And always remember to put the temperature in Kelvin. The next equation, or next relationship, Avogadro's law. This is where Avogadro actually did his work. You'll remember that when we learned about Avogadro's constant last year, I told you that Avogadro didn't actually count how many atoms there were in a mole. It was named in honor of him. Well, this was the work he did. And you might think it's fairly trivial, but at the time, in the 1700s, it was pretty substantial that as the amount of gas increased, the volume of the gas increased, assuming temperature and pressure are constant. So we get N is proportional to V, change it to an equality, V over N equals our constant, and then comparative situation, V1 on N1 equals V2 on N2. Now, we can put it all together, and this gives us the combined gas equation. So, when we put it all together, we get P1 V1 on N1 T1 equals P2 V2 on N2 T2, which is a bit of a mouthful. Most of the time, you're going to be talking about the amount of gas being constant and its pressure, temperature, or volume changing. So when the amount of gas, N, is constant, we get this rather nice relationship. P1 V1 on T1 equals P2 V2 on T2. And that is a super useful way to remember those three laws together. Matter of fact, you can ditch the other ideas and just put it all together and remember this one. But this is only for comparative samples when the conditions are changing. We haven't yet learned how to work out the moles of a gas by itself. That is coming up. So before we look at any old gas, let's think about a particular situation. And the particular situation that you really need to worry about is called SLC, Standard Laboratory Conditions. This is the one that the VCE is focusing on these days. I include STP in my notes, but really you're not going to see examples related to that. So just focus on SLC down here. So the molar volume of a gas is the volume of 1 mole of the gas. Remembering it can be any gas because, you know, they're just particles at this stage. We're not giving a mass to it. So when we've got these standard laboratory conditions, standard meaning everybody understands that SLC is 25 degrees Celsius, which is 298 Kelvin, so that's 25 degrees C, and we say 100 kilopascals pressure. That's our standard conditions. So when that's the case, 1 mole of a gas has a volume of 24.8 litres. Now we can work this out using a formula that we haven't learned yet. So I'll return to this. I'll return to it later. So the equation, and once again, this is in the data book in Table 3, the chemical relationships. The equation that you can use for SLC to work out moles of a gas is N equals V over Vm. So V is the volume of the gas. V is the volume of the gas. And Vm is the molar volume. So that's the 24.8 litres. So you may recognise a similarity with your equation for working out the moles of a solid, where you had amount N is equal to mass over molar mass. So now we've got N equals volume over molar volume. Here's a worked example for that. Pretty straightforward. I won't go through that. I think you can see where the numbers have been subbed in. And we get to the universal gas equation. Now this is your multi-purpose, don't leave home without it equation. Once again, it's in the data book in Table 3. The equation has come from those relationships that we put into the general gas equation, and now we're giving the constant a value, and it's called the gas constant, and its value is 8.31 joules per Kelvin per mole, and that is in Table 4 of the data book. So we get PV equals nRT, or if you prefer, amount in mole is equal to PV on RT. And so you can calculate the amount in mole of any gas at any pressure, any volume, any temperature, as long as your temperature is in Kelvin. And here's an example using the the ideal gas equation. So convert your units, rearrange the formula. In this case, we're being asked for volume. So volume equals N times R times T on P, and then put the numbers in, and there you have it, 30.1 litres. Right, there's some examples to try, and just looking to see, yes. So at the beginning of the next video, I will go over the answers to these examples. So this video we're running out of time for it. So we'll stop. You do those examples, and then at the start of the next video, I'll give you the answers.